Hello everyone, I'm Chanho Shin, a PhD candidate in University of California, San Diego. Today I'm going to talk about the shortwave infrared conversion imager with improved detectivity. First, the infrared ray is classified by its wavelength range, such as near IR and shortwave IR. Also, midwave IR, also near IR is from 0.7 to 1 micrometer, and shortwave IR 1 to 3 micrometer. Normally, this IR, the near IR and shortwave IR are used in biomedical imaging because of its narrow band gap. So often comparing the near IR and shortwave IR in terms of the penetration depth to human body, shortwave IR, SWIR shows deeper penetration depth to human body compared to near IR. Watching the image taken by the image of the mouse eye taken by both IR, the shortwave IR shows better contrast and sensitivity and better resolution. And based on the characteristic of the shortwave IR, the shortwave IR is used in organic photo detector because organic photo detectors have a greater advantage in terms of the biocompatibility and flexibility and low cost and solution process, simple process. And these SWIR organic photo detectors enabled by Berkeley junction of the acceptor and donor. Due to the large contact area of the acceptor and donor, the photo response is highly increased. In this work, I use the CDT-TQ as donor and PCBM as acceptor. And next is, what is the conversion imager? A conversion imager is the back-to-back diode of consisting of the photodetector and OLED. When we see the operation mechanism of the conversion imager, the incident points are converted into the electron hole pair, and generally hole pairs, generally hole charges are transferred to the OLED along the interlayer. And these transferred hole charges are recombined with the electron from the cathode. So the information obtained from the detector can be visualized in OLED as visible way. This image shows the conversion image of the skin, the skin and vein on the hands. This green region shows this green region that represents the skin, and the dark region represents the vein of the hand. If the vein is squeezed by hand, there is no blood in the vein, so it turns into the bright green color because it doesn't have the blood in the vein. As you know, the blood absorbs the infrared energy, but if the hand detached from the vein, the blood blood is peeled again on the vein, and the vein turns into the dark color. But there is a limitation in a conversion imager with SWIR organic photo detectors, because the photo-generated charges were lost by recombined with injected charge from the cathode. So electron blocking layer is needed between the photodetector and OLED. And considering the electron blocking layer, the two requirements are needed. The first layer is the blocking the charge injection from the room level, and the second layer is the transferring the charge by home level. Based on these IEEE requirements, we chose these three electron blocking layers such as NPD and TAPC and spiral or ETAP. And each layer tested with each electron blocking layer tested in sphere organic photodetectors. The first result shows the current and voltage characteristic in terms of dark current and photocurrent. The black line represents the device characteristic of shows the characteristic of the device without electron blocking layer, and the various colored line represent the device with electron blocking layer in both plot. Based on the energy level of these three electron blocking layers, these three electron blocking layers have similar room level and similar Homo level. So the dark current shows the similar device characteristic. These three devices, the devices with each electron blocking layer shows similar device characteristics in terms of the dark current. Also, the photocurrent also, these three devices shows the similar characteristic in terms of the current. But due to electron blocking layer, the dark current is lower than the conventional device. I mean, the device without the electron blocking layer, and the photocurrent is suppressed because of the energy level mismatch between the oxide and this electron blocking layer. So to analyze the detectability, we measure the noise current of each device, and in the same way with the previous result, the device with electron blocking, the devices with electron blocking shows similar noise current, but the noise current of the device without electron blocking layer shows higher value than the other device. Also, in case of the detectability, the devices with electron blocking layer shows higher detectability compared to the device without electron blocking layer. And among these three devices with electron blocking layer shows similar detectability because of the similar LUMO and HOMO level. Based on the previous result, we fabricated a conversion imager with an EV layer. And the luminance characteristic was measured. The first in the dark, the luminance of the luminance in the dark condition shows the luminance suppressed until 5 volt. Luminance in the dark was efficiently suppressed until the 5 volt, but in case of the luminance under the light intensity of the 5 milliwatt per square centimeter, it was highly enhanced by the light. Also, this plot shows the higher contrast between the light and dark. And based on this result, we demonstrate the conversion easy, and the word UCSD shows shows higher contrast at the applied bias of 5 volt, and photon efficiency reached 0.08% at 6 volt. But there was no luminous signal from the device without electron blocking layer. In addition to the conversion integer with the NP layer, we also increased the photon-to-proton efficiency by the photon multiplication effect, and this photon multiplication effect was enabled by the heterojunction bilayer of the tin dioxide and copper thiocyanate. When we see the operation mechanism of this, the heterojunction bilayer, under illumination, the general charges, these electrons are accumulated in the copper thiocyanate layer because of high LUMO level. And because of these, the accumulated charges, then the bending is occurred in n-type interlayer. Also, the injective charge can be tunneled into the BHJ layer. But on the contrary, in case of unlike is under illumination case, in the dark, charge cannot be tunneled into the detector side because the bending is not occurred. So based on this operation mechanism, the proton-to-proton efficiency can be increased twice compared to the previous conversion image. So it reached the proton-to-proton efficiency reached 0.4% and the applied bias of 8 volt. And when we compare the two devices, I mean the single layer and heterojunction bilayer, the heterojunction bilayer conversion device shows the better contrast and sensitivity. So we introduced the electron blocking layer between the sphere detector and visual OLED to block the charge injection and prevent the combination in the BHJ photosensitive layer of the detector. Also, blocking reduces noise and improves detectivity, and the proton-to-proton efficiency increased twice by the proton multiplication originating from the heterojunction bilayer. And acknowledgement from EngLab and collaborator, the Dr. Jason Azure. And thank you for your attention.